Alternating series. Any series whose terms alternate between positive and negative value is called an alternating series. An alternating series can be written in the form of the sum from n equal 1 to infinity of negative 1 to the exponent n minus 1 b of n, or the sum from n equal 1 to infinity with negative 1 to the exponent n b sub n, where b sub n is greater than 0 for all positive integer n. The alternating series test. So how do we test for the convergent divergent? There are two things that we need to take a look at. It has to satisfy that b sub n plus 1 is less than or equal to b sub n for all n. And the limit at n approaches 0, the b sub n is equal to 0. The proof of the alternating series test is written here for you, so that so you could take a look at this on your own. The one thing that I want to point it out is the sum here, based on this fact. Let's just start with a picture. So we start out at 0. Then we get s of 2, s of 4, s of 6, and s so on here and so far. Then s of 5, s of 3, s of 1. So the sum here, this here is called the b1 term. So here's b sub 1. This is where b sub 2. And this is negative b sub 3. So on and so forth. You keep the series keep getting smaller, right? Let's keep getting smaller. So as this b approaches infinity, b sub n approaches 0 according to the sum. So take a look at what the proof, and you see that picture will make sense. Determine whether the series is convergent or divergent when we use the alternating series here. So first of all, we have the sum from n equal 1 to infinity of negative 1 to the exponent n minus 1 times n. So let's write out our first couple term. When n equal 1, here we get 1. When n equal 2, we get negative 1/2 plus 1/3 minus 1/4 plus so on and so forth. So this condition, you note that b sub n plus 1 is less than b sub n, so that the first condition satisfied. The second condition, the limit at n approaches infinity of b sub n is equal to the limit at n approaches infinity of 1 over n. This equal to 0. So the second condition also satisfied. With these two conditions, we can conclude that the series n equal 1 to infinity of negative 1 to the n minus 1 over n converge. By the alternating test. what the name, alternating series test. In the second case, again, let's start with write out first couple terms. When n equal 1, I get negative 3 divided by 3. When n equal 2, we get positive 6 divided by 7. When n equal 3, we get negative 9 divided by 11. When n equal 4, 12 divided by 15. Okay. So here, the first condition, b sub n minus 1 plus 1, b sub n plus 1 is less than b sub n. The second condition, the limit at n approaches infinity, the b sub n, equal the limit at n approaches infinity of 3n divided by 4n minus 1. This equal the limit at n approaches infinity, the 3 over 4 minus 1 over n. This equal 3/4. So this is not 0. It did not satisfy the second condition of the alternating series test. So divert by the alternating series test. In the next problem, again, let's go ahead and write out the first couple terms. When n equal 1, we have 1 divided by 2. When n equal 2, so 2 plus 1 make 3, so that's negative. 2 squared make 4. 2 to the third make 8, that's 9. Plus, when n equal 3, 3 cubed is 27 plus 1 make 28. So here again, the first condition, b sub n plus 1 is less than b sub n. Second condition, the limit at n approaches infinity of n squared divided by n to the third plus 1 equal the limit at n approaches infinity of 1 over n plus 1 over n. Let's go ahead and divide top and bottom by n to the third. So the numerator becomes 1 over n divided by 1 plus 1 divided by n to the third. This equal to 0. So both conditions satisfy. So this is converted by the alternating series test. The alternating series estimation theorem. If S equal the sum of the series, then this have to satisfy that 0 less than or equal to b sub n plus 1 less than b sub n, and the limit at b sub n of b sub n at n approaches infinity equal to 0. Now if we let r sub n is the remainder, then the remainder is equal to the sum minus the sum to the n term. It has to be less than b sub n plus 1. Okay. let's estimate the sum to 3 decimal place. Here we have the sum of n equal 1 to infinity of 1 minus of negative 1 to the n divided by n factorial. Now we want to estimate this correct to 3 decimal place, so let's go ahead and start with the first two conditions. Let's write out a couple terms so we can see that the condition satisfied. So when n equal 1, we get negative 1 over 1 plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial. So note that the first condition, 0 less than equal b sub n plus 1 less than equal b sub n. The second condition, the limit at n approaches infinity of b sub n, that is 1 over n factorial, that equal to 0. Okay. Then now I want to estimate the sum. So let's go ahead and write out the first couple terms to see what happened. So s equal negative 1 plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial plus minus 1 over 5 factorial plus 1 over 6 factorial minus 1 over 7 factorial. And I'll use my calculator to estimate this sum. So far to the 7th term, I have the term b sub 7 so let's see what is the term b sub 7 get us. So b sub 7 equal 1 over 7 factorial, and this is equal to 1 over 5040. Okay. And this is less than 1 over 5000. And this is about 0.0002. So that is a really close estimate right there. Now, note that if I go ahead and add all the sum up to b sub 6. So s sub 6, if I add them all up, this is about 0.368056. So by the alternate series theorem, the remainder here for the 7th term, that then equal s minus s sub 6, right? And it have to be equal, less than equal b sub 7, and it's less than 0.0002. I can't really find the exact sum, but I know that this sum here up to the 6th term have the error of less than 0.002. So that is a pretty good estimate of what the sum would be. So then we can say that, all right, then s is equal to 0.368056 with an error of 0.0002. In the next case, well, we have this series of n equal 1 to infinity of negative 1 to the n plus 1 divided by n squared. So let's go ahead and see if we can estimate the sum here. I'll go ahead and try to see if I can estimate this using 10 term, the sum of 10 term. The more term you use, the more accurate you will get to the sum of the actual series. But let's just use 10 term here in this case, and I'll use Excel. Okay, start with n equal 1. So here's n 1. And I want to continue to n equal 10. And I will add, so the formula for the series is -1 to the exponent n minus 1 divided by n squared. So I enter it in exactly as it equal power. The number is -1 the power is n minus 1, and we divide by the power of the number to exponent 2. So that's my first term, and that continue to the 10th term. So this telling me, let's go ahead and see what else. What is b sub 11 will get us? This is b sub 10 and b sub 11. Okay. Now let's go ahead and find the sum of s sub 10 that equal the sum So here, what do we see? So let's go ahead and write out everything that I have here. So I can see that, let me move this out of the screen. What I have here, first of all, the condition is satisfied, b sub n plus 1 less than b sub n. And as you can see that the limit at n approaches infinity, the 1 over n squared is equal to 0. Okay, and note that b sub 11 is equal to 0.00824. Okay. And s sub 10, as we calculate using Excel, is 0.817962. So if I use the remainder, if I look at the remainder for 10 term, that equals s minus s sub 10. Excuse me. Remainder for what? 10 term. Remainder for 11 term, I mean. Then it would be have to less than b sub 11, right? And so this was and this is what less than, and b sub 11 is less than 0.008. Sit 5 here. Okay, so then I can estimate the sum is about the sum of s sub 10, that is 0.817962. with an error of 0.00865. So that is a very good estimate.